Let's begin today's conversation by a little bit reviewing yesterday's conversation in the form of an exact example. Now, this example I'm going to talk about, you heard me referencing yesterday. It's known as the twin paradox. Now, what is crazy is there are two insane things that you see out of the twin paradox, one of which we have already discussed in this particular class. Those insane things are not paradoxical. They are the direct result of kind of this logic that we have used. If the speed of light is constant, this is the direct result. Has to be the direct result. This is what occurs. So the first of which we discussed yesterday, time dilation. Time dilation is weird. Weird is not paradoxical. Okay? So at the end of the twin paradox today, we will discuss the paradox, but I want to be very clear that the time dilation and blank thing to be entered here later, these two things are not the paradox, even though they're weird. Okay? If you remember the example I gave yesterday in which an object went up and came back down and came over here, that was paradoxical because you were looking at the same event, but one object definitely went further. So how did they take the same amount of time? Kind of breaks our normal level of logic. And we, of course, got to the fact that one is going faster than one on the right because you don't see the velocity x. And relativity ideas kind of fix that particular paradox. Okay? Now, some paradoxes, to kind of put this out here, are human-made. Okay? And that we can understand, human-made paradoxes 100% can be just naturally paradoxical, cannot be broken. It's the argument of the next statement that I'm going to say is true. The sentence that I just said a second ago is false. That is unbreakable paradoxical. That cannot exist, right? Because if the next statement is true, that makes the next statement absolutely true. And then so I say that last statement is false, which has to be true because of the previous sentence, but you go, wait a minute. Then if that statement is true, that the last one was false, then that one is false, in which case this one can't be true. And it gets into this big circular line of logic that is kind of, but again, that is human-made. Paradoxes that we have found thus far in science do usually, as we have found them, have a solution. Okay, kind of a thing that we don't think about normally and how it breaks down. All right, so let's get on to the twin paradox. What we're going to do is we're going to imagine a planet, we'll just say Earth, okay? And on this planet are two twins. For the sake of simplicity, we're going to call this one that stays on Earth Go Slow, okay? And then the exact same twin is going to get into a rocket ship that takes off at 80% the speed of light. We talked about yesterday, the velocity is 0.8 c, and we'll call this guy Speedo. Okay? And Speedo is going to travel to a planet, star, whatever, that is 10 light years away. Now, when I say 10 light years, just since we haven't talked about this yet, of course, this is also, what is 10 light years the measurement of?
Distance. Long
distance. Correct. So this is a fraction of c. You'll notice velocity in this case is in meters per second, right? I'm going to write 10 light years. We've used this equation a lot already, but essentially, similar to what we did yesterday when creating distances out of velocities, we're going to do something very similar, okay? What is 10 light years? Well, I put 10 years here and c right there. So you're going to see me list the distance as 10c. Now, I don't put up years up here like I should typically, but that's why 10 light years, if I put years into a amount of seconds, we would get this in meters, and this is definitely a distance over here. I only highlight that because these two, 0.8c and 10c, appear on the outside to be the exact same thing, but they're decidedly not. This 0.8c is a velocity, that 10c is a distance. All right, so Speedo goes out at 0.8c, leaves and comes back, and meets Go Slow. What is the difference between them then when they, let's say they both start at 20 years old? Speedo is now younger. Let's talk about how much and see if we can't figure this out. For starters, How much time did it take? Well, we can use some relatively basic physics, okay, to do this. Actually, oops, I do need to take one aside. My apologies, I forgot this thing that we need to establish first, okay, that's really going to help us in understanding kind of the ramifications. So Einstein, I want to be very clear about Einstein because I think that he's talked about in kind of a very almost like supernatural way when you've heard about him and you haven't got into a science class. Now, I don't want to take away the fact that Einstein is ridiculously intelligent because you can get into kind of the backwards of this and people manipulate his past and it's like Einstein failed math. Not quite when you look at it accurately, it's a whole other thing. Now, that being said, I will tell you that Einstein was not particularly great at math. He himself would actually check his math by passing it off to his wife, who was much better at it and would check his math to make sure that it was actually correct. And she was much... Sure. Okay, yeah, okay. So, but here's the true thing about Einstein. And the other crazy thing, Einstein did not invent something new that other people had not already known about, okay? Here's the real genius of Einstein, as it were. Basically, here's what it came down to. At the time, everybody knew what Einstein knew. And arguably, everybody else sort of treat it more intelligently to a certain degree than he does. Okay? Here's what they know. They know all of physics. Okay? All of Newtonian physics. They have stuff in here about fluids and sum of forces and momentum and energy. Even deeper than we have probably discussed. They know a lot of this information. And what really is the thing is that at the time they are struggling. Because out of that math and Maxwell and Faraday figure out one piece of information that is really bothersome, and that is this: light goes at sea. So the problem is that everybody at the time had was pretty much, you could believe all of physics as it stands, or you can believe that. Now, when you think about it logically, if I told you that, if I said today, I just read an article online that said this crazy fact that breaks absolutely all of physics, what should and naturally should be the response of most physicists and scientists?
Yeah, that's funny. I'm not wrong.
We'll wait and see, right? Maybe not, like, I don't think it's ever a smart idea as scientists to say, like, no, we don't like it. But at the same time, let's wait until the experimentation backs it up. Einstein basically just did this. He said, you know what? Let's look at this, say this is the case, and see how it breaks the rest of everything. Let's see what happens. He does it. He does all this crazy work. He does the work that I'm looking at, that you were going to look at today, and then some. And then the interesting thing is, actually, after he writes this paper, Einstein is a genius, probably not necessarily because of this paper, but because of the year 1905, he wrote 4 ridiculously famous papers. The one that we're about to talk about in special relativity is actually, I think it was his, I don't know if it was his first or second, but it's not the one that won him the Nobel Prize, actually. Not at all. This actually didn't win him the Nobel Prize. That was Brownian motion, which we don't need to talk about. But the crazy thing about it is that. So let's review essentially. Here's what Einstein said at the beginning. He said, we're going to rely on this, and then let's see what happens. And here are what are known as Einstein's postulates.
How many are there?
2. Number 1. Light travels at sea for all observers. No matter where you are in the universe, no matter what you're doing, no matter how fast you're going, no matter how many siblings you have, light will travel. You will always measure light at sea. Yes?
What's the definition of a postulate?
These are the things he's going to hold. He's going to say, I'm going to stand on these things and see what happens. Okay? Number 2. I'm going to kind of put this a little bit more general. I can give you like the official way of saying it. You can look up Einstein's postulates and we'll be kind of in a much more official fashion. But here's what I got. The laws of physics will be agreed upon, use lighter letters there, right? By observers at the same inertial reference frame. Which is a fancy way of saying they share the same velocity. So we all currently share the same inertial reference frame because we share the same velocity. To put perspective of something that you have seen already in physics that does not share the same inertial reference frame, okay? Imagine that you've got a person sitting in a car, okay, that is driving. Okay, here they go. Is the car driving forward? Okay, they're sitting in a car right here, viewing forward. Okay, and then they begin to turn. Now we, as I've drawn this picture, are viewing them from above. We are viewing them from the Earth's reference frame. Okay, to us, what does the person do when the car starts going around in a circle?
Goes the other way.
No, not to us. Nope. To us, we would assume the person goes straight. In the inertial reference frame, so in the other frame, meaning what if you're sitting in the car? I think some of you answered this already. If you're sitting in the car and someone swings the wheel to the right, what does it feel like you do? It feels like you go to the outside. So that appears to be a fictitious force, and that fictitious force is known as centrifugal force, which we discussed all last year. It's not a force, right? It's only because they're in this reference frame that it appears like there's a force going outward, when, like I said a second ago, what are they actually doing? Right, from the reference frame of being on Earth, we can see they're going straight. From their reference frame, being in the vehicle turning right, it appears like they're thrown to the outside. Here's another example of the, excuse me. Here's another example of non-inertial reference frames. Imagine you have the globe, okay, like this, and you decide you want to throw something, and I mean when I say throw something, really, really straight that way. What's going to end up happening because of that is it's actually going to spin. Ooh, I got to do this right. Hold on. Actually, I want to go the other way. I want to go down. Okay. The Earth is spinning towards the what? East or west? East, right. It sets, it opens up in the east, so there we go. We got it going east right here, right? And are all parts of the globe going the same speed? No. Which one's going the fastest? The equator. How come?
Because it's fatter.
A little bit different.
Because its diameter is largest at the equator.
You're right there, okay? Basically, it's got to go, they have the same angular velocity, if you remember from last year, right? They cover the same amount of angle, but when you look from the top of a globe, why is the equator traveling the fastest? Simply put, farthest to go. Yeah, more distance to cover. So, what happens if you have an object that is thrown south is it is going to appear to go that way. Okay? You could see the same type of thing, by the way, if you're ever at a merry-go-round and you spin the merry-go-round and you attempt to throw a ball or roll a ball off the edge. Is it going to appear to go straight? Nope. It's going to appear to curve for these exact same reasons. I have a video on this that I'll show here that I think is kind of interesting as well. This is known as the Coriolis effect. It appears to have this weird force because it's not in the same inertial reference frame. From the outside of Earth, in this inertial reference frame, we can see, oh, it's just turning because the world's going at different speeds. But if you're on that same speed, you don't see that speed, so it weirdly feels like a bullet. It's like if you were to fire a bullet right now that you could track the whole time, and you were to fire it south, would it go straight south? No, it would not. It would curve, I believe, towards the east because of this particular Coriolis effect. Right. Coriolis effect is also the reason why when you look at hurricanes, they spin one direction in the northern hemisphere and spin the entire other direction in the southern hemisphere. Quick aside, a lot of people also put that in the same category of, well, toilets spin one way in the northern hemisphere and the other way in the southern hemisphere. In actuality, that is 100% not true. The only way that toilets spin a particular direction, because there's such a small distance, Coriolis effect is not going to have any impact. If you look, the main reason your toilet spins is because there's jets on the top and water pushes a particular way, and that's the only reason they spin that particular way. There's a great Veritasium that does this exact same conversation. It's not so true. Anyway, but point being, as long as we share the same inertial reference frame, we should agree on that entire book of physics that we said earlier, right? So, that's previous class. Go slow. If Go Slow is having conversations with like everybody in his family that has stayed on Earth, okay, they will all agree about how physics works. And Speedo, let's say he's joined by 2 or 3 other individuals, everybody on that on that thing would agree on how it works. Meaning, simply put, will Speedo experience time at the normal rate? Yeah, because how fast is he going compared to himself?
None.
0, aka he's in the exact same inertial reference frame as his body. 1 year is 1 year is 1 year, right? Go slow. Also at 0 to himself. So should experience 1 year is 1 year is 1 year. There will only be a breakdown when Speedo and Go Slow get back together and have a conversation about how time traveled, in which case you're going to get that weird ratio in this particular case. So, how do we figure out how much time this is going to take? Really basic physics. How much distance does Speedo have to go to get there and back? Try again.
20 light years.
20 light years, yes. How do you get 20 light years?
10 times.
Yeah, so we're just going to take simple stuff here. We're going to take 20 light years distance, divide by the velocity that he's at. What velocity is he at? 0.8 c. So how long should it take Speedo to travel this 10 light years? 25 years. All right. So let's say, for sake of argument, they probably wouldn't make somebody lower than 20-year-olds are probably not getting on this. So we'll say 30 years old. Let's say the twins began at 30 years old. So now, as they come back, Speedo is 55 years old. Who got time proper? Which time is
Go
that?
slow.
Why? I heard 2 different arguments, so don't talk to me, battle each other. A little bit, yeah.
Speedo is the one moving. Go slow is not. Go slow is.
I agree with what she said. Why do you disagree?
Speedo is the one that is moving, but Speedo is the one that has the event happening.
Okay, I do disagree with actually the same thing that you guys both said. Actually, I take back what I said. Who's moving?
Speedo.
Who's moving?
Well, it's no. It depends on what frame you're looking at. Like in relation to who.
Thank you.
Speedo
You guys
is
naturally did the thing. You did the thing, and I always want to catch you when you do. I didn't catch you when you did it earlier, so I apologize for not catching it right away. What is the thing that you did that I have issue with?
We assumed who was moving.
Why? What did you assume? To assume that he's the one moving?
Because you gave Speedo a velocity. but
Sure.
not slow.
But that's just relative to
Because Speedo is something that moves.
the thing that you did that I'm going to take issue with is you assumed Earth was 0. Right?
Yeah.
So who's moving?
Everybody else.
Depends on who you ask.
Yes.
Let's try this differently because I think this will help. What will Go Slow see? Assuming you can see this the whole way. Obviously, it's crazy distances. That's unreliable. But what would Go Slow see Speedo do?
Move really
Leave
slow.
and come back.
Yeah. Leave, come back. Very good. What should, and this is an important thing to get, what should Speedo see Go Slow do if he's got a window out the back?
Go slow going that way and coming back.
Correct. So who's moving? Depends on who you ask. So why? So let's go back to who gets time proper and why.
Depends on who you ask.
Assuming
No, there is a correct answer.
Assuming Go slow is at rest to the event.
What's the event?
The event of Speedo leaving and coming back.
So the event is speedo and
Leaving
leaving and coming back.
Coming back.
So who's at rest of that event?
Go slow.
Speedo.
Speedo is?
The event you just said. Listen to what you said. You said the event is speedo going out and
Go
coming
slow
back.
watching Speedo leave and come back.
The event is speedo going out and coming back. Though. So who's at rest to speedo going out and coming back? Speedo. Speedo is going the exact same speed as the whole thing that's going out and coming back. So this time here is time proper. Do the math from yesterday and now tell me how much should time dilation be. Take 5 minutes, do the math real quick. Please do the math on your paper and enter your calculator.
So gamma would be 25, right?
25 should be time proper. So our equations from yesterday are this. Time dilation is equal to time proper times gamma. Remind me real quick what gamma is equal to.
1 over the square root of 1 minus b squared over c squared.
And I said this yesterday, and I haven't done a great job of doing this in the past, and I think it's very helpful. That yes, this is the mathematical definition, but actually a better way to understand gamma is right here. That gamma is simply the ratio of those two, right? But in this case, like yesterday, I gave you an example where I said, you guys are going to get 22 years, I'm going to get 1 year. You knew both of these, so you could easily go, oh, that's 22, right? Do we know those two times in this particular case? No, you don't know time proper. You don't know time dilation. You only know time proper. So now we use this equation right here with 0.8c in order to figure out. Actually, I think we did this one yesterday, didn't we? Please do the math on your paper because you're going to need to do it on the test. You might as well get good at it. That does not look like a gamma, I apologize. Let me try to do it. That's about the best gamma that I'll ever do, by the way. That one.
It's not just a V.
It's not just a V, no. It's actually it's kind of a curly down, and at the very bottom you do like a little drop thing, but that's not good either. Here, let's do this. Microsoft Word. If ever you want to know what one is, it's probably best to go and
If you go to accessories,
do what now?
Windows accessories,
What was that just now? Windows accessories. Oh, thank you.
character map.
Sure. Yes, we can do that. I don't have Word on there. We not have Microsoft Word on this?
It might just also be called Word
Sure.
under the W's.
I didn't think I saw that. Oh, there it is. My apologies.
For gamma? 1 or 1.6. I got 1 per gamma.
So here it is. If you ever want to see what it is, you can go to symbol. And when I wasn't very good at these, I'll tell you what I did is I just kept typing in a bunch of letters until I found it. There it is. It's just G. There it is.
Wait, what did you say? What?
That's it. That is a gamma.
You do symbol and G?
That's a gamma. Simple. Yeah. Just like if you want sigma, there's a lowercase sigma, there's a capital sigma. There's a lowercase pi, there's an uppercase pi.
Uppercase.
Since when did they have uppercase pi?
They have uppercase everywhere.
Yeah, it's an alphabet.
Like if you go to Greek houses, they always use capitals. So if you say like, if you go to pi sigma alpha, this is what it's going to say on the board. It's going to say pi sigma alpha.
I did not know.
Actually, usually alpha they do cheat, and they usually do alpha. But alpha is in fact just capital A. Do you know why, by the way, it's called the alphabet?
Because it starts with alpha.
Because the letters were brought about by the Greeks, and what are the first two letters of the Greek alphabet?
Alpha and beta.
Alpha and beta. So they basically, Greek parents would ask their kids, "Hey, tell me your alpha betas," and that just got shortened alphabet.
Now it's ABCs.
Sure.
The C.
Oh, there's this is a weird one that it's not usually known. There's your theta, but actually that one's actually put that on Q because over on T they have tau. Remember tau from school. All right, so what do we got? What's the gamma factor?
I got 41.67.
No. Oh, I'm sorry. No, sorry. What's
Oh,
gamma?
the gamma
I think-
factor 1.67.
Yeah, so 1.67 5/3. Okay, here's the math real quick. Here's what I want you to plug in. 1 over the square root of 1 minus 0.8 c squared over c squared, right? So then you punch it in your calculator. The c squareds, of course, are going to cancel each other out. And I think we did do this one yesterday. 0.8 squared is 0.64. 1 minus 0.64 is 0.36. The square root of 0.36 is 0.6. And then 1 divided by that gives us 1.67. Or actually, I'm going to shorten that to 5/3. Let's make numbers a little cleaner here. I don't want to use 20 light years. I'm changing my mind. Because it doesn't matter. 5/3 is going to stay the same either way. But you just said 5/3 of like 25 years is some stupid number, right?
41.6.
So let's say, hold on, let me try this.
It's 125.
That'll be cleaner. Will this be cleaner? Hold on. Yeah, let's do this. Okay, let's do this because it'll just be nicer on the numbers. Let's say that instead of 10 light years away, it started off with, let's say it was 6 light years away, which doesn't change a whole lot. I'll show you real quick. So, I just did that. Okay, 6 light years away. So that makes this guy what? 12 light years.
Gives us 15.
Yeah, that's a little bit nicer of a number, 15. And then when you put 15 into here, time dilation is going to be gamma times. Actually, no, I screwed that up. Oh, that's what I did. And now what's time dilation?
15
Divided by 3.
25.0.
25. All right. So, Speedo goes out. They both start at 30 years old. Speedo goes out. He leaves. He comes back and he says, why are you so old? I'm only 15 years older. I'm 45. Okay? But he looks at his brother, and how old is his brother? 55. 10 years to separate them quite a bit. And if you check their organs, and if you check absolutely everything, if you check their tissue sample, there's no magic to this, there's no trick to this. Yes, Ghostlow is older than his twin brother by 10 years due to time dilation. Now, they start to have an argument with one another because they start to look at Einstein's second postulate, in which physics should agree for both parties. And so, Ghostlow looks at the situation and he goes, well, hold on, did I do that right? Oh, shoot. I might have done that wrong. No, that's right.
If it's wrong, then I don't need to freaking know.
Hold on a second, because it matters with what we're doing in just a second. Yes, I got it. Okay. Or do I misled you about who gets the 15 years. 15 years, I am wrong. I apologize. 15 years, and I'll explain how I know this in a second, so you get to this. This actually is time dilation. Okay, this would be what Ghostlow sees. So math is still pretty much the same. The only thing that changes is right down here, rather than Speedo going this, Ghostlow gets that. So Ghostlow is now 45, but his brother is how older? Well, we can measure time proper. Time proper is time dilation divided by gamma. Yes, that's right. Okay, which is 9 years. So it's still the same type of deal. Okay, who's getting time proper? Still Speedo. I'm not wrong in that. Okay, but the Speedo gets 9 years. Now, I press this because there's a thing that comes up and happens now. So here's what happens.
So Speedo gets time proper.
That doesn't change. Yes, Speedo is getting time proper. I just had it wrong who was getting the 15 years. And I'll show you how I know in just a second. Okay? So here's what Go Slow says. Go Slow says, I don't understand. You went out 12 light years. You're traveling 80% the speed of light. He goes, this is some of the dumbest, most basic physics there is. If you're traveling 80% the speed of light and you go 12 light years, it should take 15 years. And he will go, everyone on Earth will agree with me that that's the case. And Speedo looks at him and he says, yeah, I agree with you that that's the case. But Speedo goes, I didn't travel 12 light years. He goes, what are you talking about? Look out the window. And somehow apparently they can measure this light years from the nearest planet. So it's right there, it's right there. 6 light years there, it's 6 light years back. And Speedo looks at him and goes, I agree with you now. I agree with you now that I'm standing on Earth, that it's 6 light years away, but check my freaking odometer in the rocket ship. What does my odometer say? The odometer says not that it was 6 light years there and 6 light years back. The odometer says that the distance between the planets when he was actually traveling at the percent the speed of light is actually smaller. So, if I use this guy right here, if I use that guy right here, Speedo goes, let me do some basic math for you. How far did I go? It's just distance equals velocity times time, man. He goes, I agree I was traveling 80% the speed of light. But as you can clearly see from my skin and everything about me, I am not 15 years older, I am 9 years older. So if I just multiply this out, I get that the whole trip was 7.2 light years. It wasn't 6 light years to the most recent planet. It was only 3.6 to the nearest planet. Make sure I did that right real quick. I did that math in my head. Yeah, you guys are right. Meaning, when Speedo went to the nearest planet, he had to deal with something by the name of length contraction. So, crap. That means that if you are traveling to Chicago at a very high velocity, and again, I'll remind you that yesterday we found out that if you go 10% the speed of light, we're talking about 0.5%, so it's not that much different. But let's say you're traveling to Chicago at half the speed of light. Well, for starters, obviously you're going to get there quick because you're going half the speed of light. But there's a second reason you're going to get there really, really quick. And that is, not only are you going to get there quick because you're going faster, but actually by going quick, the actual distance between the two objects gets smaller.
Can you repeat that?
Sure. Let me write it a little bit differently. Let's say here's Earth, and here's some object way off in the distance. Okay, this distance L. Okay, that's the distance L. Who would measure that distance? Us. Someone on Earth. Anyone on Earth. As a matter of fact, we will call that length proper. And length proper has an extraordinarily similar definition to time proper. Length proper is defined as the length measured by the observer at rest to the length. So here we are on Earth. Here's Go Slow on Earth. Okay, here's everybody on Earth. Should everybody on Earth get length proper? Yes, is at rest. Keep in mind, by the way, if we just remind ourselves of the last situation, who got time proper?
Go speedo.
Speedo. So notice that they don't inherently go together either, right? The event is speedo going out and coming back. Who's at rest of the event? Speedo. But who's at rest of the length that they went through? Go slow, because speedo is moving through that particular length. Yes? So this is the length measured by the person on the planet. But here's what happens. When you are actually traveling a speed, I'm not sure what it is off the top of my head. I'm sure we could figure it out. But let's say you're traveling a speed in which gamma is 2. Okay? What does that mean already?
That it's
Time
going
proper
faster
is
than.
Time proper is going to be double of what t prime was.
Backwards that.
Backwards that.
So, like, let's use my example from the other day. Let's say Spainower gets in a rocket ship, goes out, comes back, and I tell you that gamma is 2. What does that mean?
We age 2 years, he waits 4.
Yeah, so you would experience for whatever amount of time you want to talk about, right? Like, if the whole trip took me 10 minutes, and it would take you, you would watch it in 20 minutes. But think about that in terms of logic. Would we agree about how fast I'm going relative to each other? Yes, we would agree on how fast I'm going. So if both of us agree on how fast I'm going, what is the only way that I would travel that distance in half the amount of time? The distance itself was half as big. So to the person on the rocket ship, this is a messy business, I apologize. The distance from the planet to this guy is half the length. Now, what you're going to have to justify in your head, which is messy here, is that those two pictures that I just drew are the same length. Yes, it is. 100%. And I reiterate what I said yesterday. If you don't find this weird, then you definitely don't understand it. The math is nice, okay? The math is this. Length contraction is equal to length proper divided by gamma. And actually, if you take that equation back to the previous example, this is where I can share with you how I knew that I was wrong a minute ago. Okay? If you take that equation back, I found the distance right here. Excuse me. I found the distance that speedo had gone by just doing this basic thing. But you could also find this exact same set of numbers by taking, who gets length proper? Go slow, or the people on the, be careful with us, because I don't know where you're putting us. In this example, go slow. And who measured the distance? Go slow. So go slow is getting 12 light years, so that would be length proper. So I take length proper, right, 12 light years. There's length proper. And I divide by gamma 5/3. What is that number? Some of you are probably going to need to put in your calculator.
36 minutes.
Because you clean that up a bit in terms of decimal. That number is that one right there, 7.2. You remember I got the 3.6 because this was the total trip, right? That 3.6 was just the distance that speedo would see the planet away. So the distance to the planet itself gets freaking smaller. So have you ever watched in sci-fi, and they kind of try to do this arguably correctly, where you get the stars and you start going really fast and the stars appear to stretch a little bit. In a way that's somewhat accurate, because what it's gonna appear like is as you speed up, what are those stars going to do?
No, like
They're gonna get closer. Now here's what's messy about that, okay? I think from an outside perspective, a general person would look at that and they would say, oh, the stars appear closer. What we are learning, which is super messy, is what's wrong about that sentence.
They are close.
Correct. When the stars come at you as you speed up closer to the speed of light, it is not that they appear closer. They freaking are closer. So earlier, the other day, I talked about the example where I said, hey, Spain-Hour goes out, gamma 22, blah, blah, blah. You've heard all this before. And one thing that we have talked about in space travel is this issue of the really large distances. When in all actuality, if we and large distances in relation to the limited amount of time that human beings can live, right? What's actually a little bit strange is if our technology does develop to where we can start to go at these fractions of the speed of light in any particular way, that's not going to be nearly as much of an issue as we might think. Because, let's say we've got a person here on Earth, okay, and we look at a solar system over here that is, to make my life easy, let's go 80 light years away. Super far away. Distance is 80 light years away. And let's say at the time we figure out that the maximum that we can go is that 80% the speed of light, what we've been talking about. Now, to somebody not understanding this, they'd go, well, that's going to be an issue. We're going to have to figure something out because according to this really basic math here, to get to that 80 light years away, traveling at 0.8 c is going to take 100 years, and human beings don't live to be 100 years long. Except what are they not considering? We don't go 80 light years away if we're actually going 0.8 c. If gamma, as we've already done, is 1.67, then that, for people on the spaceship, is not 80 light years away. It's about 47 light years away. Now, if I divide that by my 0.8, I don't have to worry about accomplishing this in 100 years. I'm only going to need to be 60 years older in order to do it, so we can answer. Now, obviously, when you're talking about low gamma factors, you're like, well, that still kind of sucks. But if we could get a gamma factor of, say, just as simple as 4, now, I say simple, if you calculate how fast that is, that's not quite as simple as I said. But if we can pick whatever velocity goes here such that this gamma is 4, then that's not 80 light years away, it's 20 light years away. And actually, weirdly, the faster and faster and faster we can go for technology, what happens to the entire universe? Gets a lot closer real fast. Now, the really messed up thing, which we'll talk a little bit more about tomorrow, is this. What happens as you approach the speed of light? Now, let's talk about that from another perspective, though, because I think this is very important. I asked you yesterday as you were leaving, I said, what if I have a spaceship that's traveling, like, say, 90% the speed of light? I think I said 70 yesterday, but this will work. 90% the speed of light, and that spaceship shoots out another 90%. How fast would you assume people on Earth see the spaceship going? 1.8, right? And if you get into faster than the speed of light, you can actually work out the math, and the math starts to work out that if you go faster than the speed of light, you actually can travel backwards in time. But here's the trick, because people want to ask me, they want to go, hey, Spain, and they go, what if we went faster than the speed of light? That's not where you want to start, because here's the real trick. How fast does someone on Earth see the speed of light going?
3 times. We don't.
How fast do people on Earth see the speed of light going?
Our velocity plus the speed of light.
Nope. C. Everybody on Earth sees light traveling at. I thought I had it up here. Where did it go?
Let's see, 3 times 10 to the 8.
Yep, 3 times 10 to the 8th meters per second. There we go. Number 1, light travels at C for who? So now you get in a rocket ship and you're traveling 99% the speed of light, and your logical person thinks, oh, well, they're traveling 99% the speed of light. Who would see them going 99% the speed of light? Which observer? On the ship or on Earth? On Earth. So on Earth, we see the speed of light going c, and we see the person going 99% c. So we go, oh, they're only 1% away. But if you were on that ship, how fast do you see light going?
See,
So how much closer are you to going faster than the speed of light? Not in the slightest. It is not a question of can we go faster than the speed of light. It is a question of can we get any closer? To get to 101%, we would have to begin by getting to 1%. We don't know how to do that, because to get closer to the speed of light is to see light itself going slower and slower and slower and slower and slower. Does it? No.
So
All
we
right.
have to slow down light to go faster.
Or find some other way around the science as we understand it right now. And this is what you're getting into, okay? Einstein says these two things, and this is what all comes out of it. You go, holy crap, he's breaking his brain in order to kind of pretty much rearrange everything that's right there. Now, quick couple of reminders so that you don't feel too bad about all the work that we put in that I basically just shared with you a second ago is broken by the fact that light is c, okay? You're going to hear things called relativistic and non-relativistic. Okay? Relativistic, the breaking point I shared with you yesterday, I'll share with you again, is about 10%. C is where they assume it is beyond that, we start to say that situations are relativistic. Because what is our gamma right now? 1. Correct. We agree on time, we agree on distances, and that's what 2 says. If I measure the distance from here to the back of the room, and you measure the distance from here to the back of the room, then we should agree. Technically, this says, if Kian attempts to measure the distance from here to the back of the room while walking to the back of the room, technically, what should he find? The distance is smaller. He should technically find that. That being said, at anything lower than 10% the speed of light, like here, I'll just do some math for you real quick using that equation that we did on this guy, right? Oh, why are you being so slow? Pressing the button. I don't have all the tabs open, okay? I'm gonna have 11 tabs to be fair. But, oh, this is the end, actually. I just have the wrong spot. That's on me. That's on me, computer. This one's me. Okay. So if I use this equation right here, let's pick a really fast speed, but it's non-relativistic. Let's say I'm going 200,000 meters per second. Okay, I punch 200,000 meters per second, 200,000 squared, and then I divide that by 3e to the 8th squared. And then I take 1 minus that, and then I square root that, and then I take 1 divided by that, and I get, for something traveling 200,000 meters per second, a gamma factor of 1.00000002222. Is that basically 1?
Yep.
Yeah. Are any of us going to be traveling 200 meters per second, or sorry, not 200, my apologies, 200,000 meters per second? No. To put this in perspective, I figured out that if you got in a car and at the beginning of your life, the very beginning of your life, and the entire time you were alive, somehow they did a magical thing and they put gas in your car so the car could keep going at 60 miles an hour, your entire life, your life would be different, assuming that you would stay the same, that you would get to the same age either way. Your life would be a half a nanosecond different. That's the difference we're talking about at these low speeds. So non-relativistic, we can just go back to a very normal assumption that, yeah, this book is 100% correct. Is it technically off? Yes, but by fractions that are over in like the 30th decimal place. So let's just go ahead and call it even and say that's not, there's other factors that are going to have way bigger impact than non-relativistic. But let's go back to this real quick. And I told you at the beginning of this conversation that the twin paradox is not that. Meaning, I told you that the twin paradox are not these two weird things. These two weird things that come out of the twin paradox is completely normal. First one being time dilation, weirdly normal. Length contraction, weirdly normal. we actually stumbled while talking about this a little bit into this paradox, and here it is. The paradox comes from relativity. Okay? Meaning, what did we say that go slow sees speedo do? Let's say here's go slow, okay, on the planet. Alright? What does he see speedo do? Leave and come back. Right? And then what does speedo see go slow do? Leave and come back. So where's the paradox?
They did.
What's the freaking event? I keep saying that it's speedo, but why the heck does speedo get the event? Can it just be that go slow is the event and he comes out and goes back? In which case everything flips. How does it appears to be completely symmetrical? Why are the results not symmetrical? And here's what it is. Okay? It has to do a little bit with general relativity, and it has to do with inertial reference frames and who actually switched inertial reference frames. And here's the way I'm gonna help you to understand this. Imagine at the moment that speedo turned around, and by the way, we're assuming he instantaneously turns around and goes the opposite direction, which is a problem for what reason?
You can't just velocity can't instantaneously change.
Sure, let's say you did. What is that called, by the way, when you change velocity?
Acceleration.
So if you change velocity in 0 amount of time, basic definition of acceleration would be that how much acceleration is required for that? Infinite. And what is necessary to get infinite acceleration?
Go speed of light.
No, not quite.
Teleportation.
No. Well, you're there-ish. What is the cause of all acceleration? So if you need infinite acceleration, every single human being on that ship is now a puddle. And I would actually argue that every bit of metal and every piece of material on that particular thing is a now puddle and is no longer a ship if it requires infinite force. So we're going to assume really quick. That being said, imagine when that happens, that speedo and go slow are both holding on to a very full cup of coffee. Okay, they're holding on to their full cup of coffee. What's going to be different about that cup of coffee the moment that speedo turns around?
And you're saying if like speedo instantaneously turned around.
They're just turned around. We're not worried about
If you
the
just turn around
But not
The coffee is gonna go that way.
For who?
for speedo.
Is go slow is going to?
No.
No. There's the difference in the symmetry. The reason why it's speedo that gets the event, it's the reason that speedo gets time proper, that is the event, and the reason that speedo gets length contraction, is the one considered to be moving, is that speedo is the one that changes inertial reference frames. Speedo is the one that changed velocities. You can tell this by looking at mass and looking at that and seeing the water spill out, because that water was continuing at a particular pace through space, but velocity we're already still seeing is that velocity is a particular pace traveling through time. If that ship went on forever, would anybody on that ship ever disagree about how time moves? None whatsoever. It is only because they turned around and matched. So here's the gist of that paradox. So again, let me reiterate, because this will definitely potentially come up on a short answer in the test. And that is, what is the paradox? It's relativity. Okay, the paradox of it is not yes, the paradox of the twin paradox is who gets time dilation and who gets length contraction, and it's based on the fact that go slow sees speedo go out and come back, but speedo should watch go slow go out and come back. The event that is the issue is when they're both out. Who actually switched the reference frame they're going through, and that is speedo, which you can see very clearly because he would spill coffee. Go slow would not have any impact on his coffee whatsoever because he has not actually changed. So again, to reiterate, the paradox is it appears to be symmetrical, so why do we get non-symmetrical results? And what we actually see from this resolution is that no, it is not in fact symmetrical because one is switching reference frames. How are we doing? It's not an easy thing to come to terms with. Obviously, it's going to take some reading on your part to really come to terms with this. The math is relatively simple, but that doesn't necessarily make it easy. Here's the next three things we're going to do. One, I'm going to show you a very old video, and you're going to laugh at how old it is in the animation, and that's fine. It's fine. But just don't laugh so hard that you miss the content, because that's why I'm showing it to you. Okay? This is a gentleman who found another way to represent time dilation than what I'm sharing with you that I think is brilliant and I think is really helpful to see kind of from this other perspective. And we've been talking about go slow's perspective. We've been talking about speedo's perspective. We're going to look at it sort of from the perspective of light itself. Okay? To try to answer. It's a 12-minute video. Humor me, watch it carefully, and we can talk about it afterwards. If you want to watch it later, I posted the link on the chapter. So it's under 26. And here we go. Maybe. Oh, there we go. Come on. Come on. Don't be slow. I believe in you. No, no, no. That is not what I asked you to do.
Hello there.
Children. All right. I mean, I can't get too mad. He's only 2. All right.
We'll see right here, gang? Right here.
Where did the time go? Does anybody know? When did the day break? Did someone drop it? Was it a mistake?
Did you know that time's different when you move at different speeds? That when you move through space, you change the rate at which you move into the future? Well, you can't really notice these differences for everyday speeds, but for really high speeds, like for rockets traveling about half the speed of light, these time differences can be noticed. Let's take a look at the so-called twin paradox.
Well, bye. I don't know. I'll see you again. Yeah, I get it. Maybe we'll see you. Sure, you know, well, it's all in the dark outside. Well, it is dark. I'll get out of line.
Now, while the traveling twin experiences weeks,
By the way, I should add to this because I think it's helpful for this. You'll notice that animators regularly take advantage of our relativistic way of viewing things. For example, as you're looking at this, I'm curious, who's moving? Like, or how did your brain perceive
The stuff is moving past the window.
you in this? It's interesting, right? Because like, and that's what I find most people would say. Most people say, "Oh, the stuff is moving past." They're using animation. Except, what is the animator attempting to get you to think?
The guy's
That all that stuff is holding still, and the rocket is moving to the right. Now, obviously, in animation, you can't do that. So, and another part of that is the reason I would say you think the objects are moving left is that they don't fill up the screen. If I were to fill up the screen with, say, you know, trees and a road and building, and now you call that Earth, I'm going to go ahead and guess, even though it's the exact same thing, all of your brains are going to go, oh, it's the ship that's now moving right, as opposed to the stuff moving left, even though it's the same thing.
the stay-at-home twin experiences years.
No, I think I'll just sit here and do nothing. Yeah. That sounds like, yeah, I'll do that. Oh, what is going on out there? Oh, my goodness. I don't believe it. I must relax. I can't relax. I'm too old to relax. Look at the size of this one, would you?
Could a situation like this be true? You bet it can. This is time dilation. We can see time dilation by comparing clocks from different frames of reference, say from the Earth and from a high-speed rocket ship. Now, a clock can be anything that measures periodic intervals of time. To simplify, we're going to let the ticks of our clock be periodic flashes of light. Look at the light flashes emitted by the stationary rocket ship. Now, some time goes by before they reach the distant planet, but since there's no relative motion involved, successive flashes get to the planet at regularly spaced intervals. That's to say, both the sender and the receiver will agree on the time intervals between the flashes. Now, there's nothing unusual about this.
Do we get that so far?
Yeah.
So essentially, if the flashes are emitted every 6 minutes, Earth should see them at every 6 minutes. Cool.
But suppose the rocket ship moves. Look at the Doppler effect. An observer sees the flashes at shorter intervals. Suppose the ship moves fast enough so an observer sees the flashes at intervals twice as short as the ship sends them. Then if the ship moves away just as fast now, an observer is going to see intervals twice as long. Like if the rocket sends a flash every 6 minutes, they'll be seen every 12 minutes by the observer when the rocket moves away. But every 3 minutes when the rocket's approaching.
You good with that?
Now let's apply this to time dilation. If the ship passes by the Earth and moves away at the same high speed for 1 hour, and quickly turns around and then returns in 1 hour, rocket ship time, this 2-hour trip is seen by the Earth as taking place not in 2 hours, but in 2.5 hours. And this is because the ship and the Earth have been in completely different realms of time. Let's look at this in greater detail. Suppose that when the ship goes by the Earth, that clocks on Earth and on the ship are synchronized to 12 noon. Then as the rocket leaves the Earth, a flash of light is emitted by the ship every 6 minutes. That's 6 minutes rocket time. Then the ship emits 10 of these.
So here's an interesting perspective to think of. Imagine you're on Earth. What do you see the rocket ship doing relative to what it's actually doing?
See the ship.
For example, like okay, the rocket's about to emit its 5th flash right here, right?
These
Okay,
6-minute flashes.
Yeah, okay, so that's the 6th one right there. So that's 5, that's 4. What should people on Earth see the rocket ship doing? Going out way slower than it actually is.
While going away from the Earth. The 10th flash is going to be emitted 60 minutes after leaving the Earth. Then the ship's clock is going to read 1 o'clock just when this 10th flash is emitted. Now suppose this is the moment that the ship turns around.
This is an
Our
interesting
Earth observers don't see the turnaround until they see the 10th flash.
Right, so the ship is kind of
Now
coming
here it
back,
comes.
but what is people on Earth seeing the ship do? These
Keep
three
going now.
these 3 flashes mean it appears to people on Earth like the ship is still going out. Yeah.
It's going to take some time for it to get to them. Closer, closer, closer. Bam.
All right. So now, what do people on Earth see?
The turnaround.
The turnaround.
And there it is.
But again, remember, those
10
are the
flashes, 12 minutes apart. That's 120 minutes, 2 hours. So that means it's 2 o'clock now on Earth. Now the 10 flashes the ship emits when approaching the Earth, they're going to be seen 3.
Way, it was 12. So 10 flashes on the ship would be
An hour.
an hour. 10 flashes on Earth would be 2.
No, 2 hours.
2 hours.
3 minutes apart, or all 10 in 30 minutes. The first is 3 minutes after 2 o'clock, Earth time. The next is 3 minutes later, and so on, until the last flash is emitted just as the ship whizzes past the Earth. And that's going to be 2:30, Earth time. So a clock aboard the rocket ship reads 2 o'clock, while a clock on the Earth reads 2:30. This checks out. Check the figures.
So yeah, so the ship is always relative to the clock. So it's always going to see the flashes go out at every 6 minutes. 20 flashes, 6 1 apart. The total trip for the ship should take 2 hours, 1 hour, 20 minutes. But for the Earth, that first 10 flashes were 12 minutes apart. That's the 2 hours. The last 10 flashes were 3 minutes apart. That's 30 minutes for a total of 150 or 2.5 hours. And if you think about, if I pull in my example from the other day, this matches perfectly with Spainhour going out in the ship at crazy fast speed for a year. And you guys getting 22
Now let's go
years.
through this once again. Watch carefully and compare the clocks.
Alright, so let's do this real quick, because I find this to be kind of fascinating. So they're going to put out the 10th flash right there. Okay? If we trace back, and this animation isn't perfect, right? 9, 8, 7, let's say it was 6 that's right here. What time is it on Earth? How much time has progressed on Earth? 72 minutes. Right? How much time has progressed on the ship? 60 minutes, yeah. Alright, let's go the other way. So there it is, there's the 10th flash getting at Earth. So 10 flashes, 12 minutes, that's 2 hours. But notice that the ship is only on their 16th flash. 16 times 6 is 96 minutes. So about an hour and 36 minutes have progressed on the ship, where 2 hours have progressed on Earth. Also, by the way, what is Earth seeing the ship doing right now?
Very fast.
Yep. And weirdly, they're going to see them go.
We'll get the
crazy
same
fast.
result if we
Not
switch
see
frames
them
of
go
reference.
faster than the speed of light.
The Earth-
Because you'll notice that that ship was never faster than one of those little bulbs coming out.
Earth will send flashes now at 6-minute intervals, and the rocket ship will observe them, while again departing and returning on what for the ship is a 2-hour journey. 1 hour out and 1 hour back. While going away, the ship's going to see flashes 12 minutes apart.
So we're flipping the script. Instead of the light being on the ship, it's...
That means it's going to see a total of 5 flashes during this hour of going away.
So on 12 minutes apart, it's going out to an hour. You saw 5
See that?
flashes.
Now while returning, the ship sees flashes 3 minutes apart. It's going to see a total of 20 during the hour of return.
So yeah, so total.
For the round trip then, the Earth emits a total of 25 flashes. At 6-minute interval, that's 150 minutes, or 2.5 hours.
Which, by the way, for Earth, it puts it 6 minutes apart, means 25.
Same results as before. So from either frame of reference, a person on Earth ages more than a person in a high-speed rocket ship. It's not so much a question of who's moving and who isn't, but rather the different space-times experienced. The person on Earth remains in one space-time throughout the experiment, whereas the person in the rocket ship is in a completely different realm of time while traversing space going away from the Earth and then still another realm of time while traversing space and coming back to the Earth. That's 2 space-times.
So a minute ago, I was talking about the solution to the paradox. Let me put something really weird to this that would make the opposite actually be the case. I said the paradox is, here's Go Slow, here's Speedo, going out, coming back. Speedo gets over here, flips around, turns directions, and comes back the other way, right? And the difference is when he turns around on the right side, he switches frames of reference. So let's pretend for a second, what would switch this? If, and in this case, let's go back to this. In this case, where Speedo does what he always does, Speedo is the event, and therefore becomes time proper. We all get time dilation, because we experience it differently, because we didn't flip through frames of time like he did. Okay? But we would also get length proper, because we would measure the actual distance. We would be at rest to what he's going through, and Speedo would get length contraction in this case. Let's say we flip the script. Let's say everybody on the rocket ship decides, you know what? We never want to return to Earth. As a matter of fact, we never want to change this velocity. Everything on this ship is amazing. We're just going to continue like normal. We're just going to go forever. But everybody on Earth decides, I miss those people on that rocket ship, and we're going to do something ridiculously dumb. So we turn Earth into a rocket ship. We leave our solar system. We put giant rockets on the back of
We
Earth. Earth.
should do this.
Now, in this particular case, who's now going to be switching inertial frames of reference? Earth is now switching inertial frames of reference. So that means that if that was the case, come on, words are hard. That by them switching, why? Why are you so bad today?
I think it needs to sleep.
Fair enough, I guess. Okay. Since we, in this particular case, along with Go Slow, decide to change inertial reference frames, we become the event, we get time proper, and actually Speedo and everybody on the ship in this case would get time dilation. If we met back up with them in this super messy business, we would be the ones that were younger because we caught back up, because we switched inertial frames of reference. And when you think about it, this distance that was between us, who is at rest to it? Them. So they would get length proper, and actually by speeding up and going a different velocity, we change the space between us and them and an entirely different frame of reference. That's the paradox, and also the solution to the paradox. Now, where does this occur? Well, let's do some math here real quick on our last example to get this. In the sky, I want to get the exact numbers here. Hold on. Because the numbers are going to be messy if I don't. Every day we get hit with this radiation. And because we get hit with this particular radiation, okay, this will work. All right. Because we get hit with this radiation, muons exist. Now, muon, for just to put it simply, is a part of the it's part of the particle spectrum of particle model of the universe, and we can, through chemistry, get when they should exist and whether or not they should exist. And actually, we can use half-lives to figure out how long they should actually exist before spontaneously popping out of existence. Now, our atmosphere is something like 9,000 meters up in the air. Okay? And muons, through the math, we've figured out that their half-life and everything, their lifetime before they cease to exist, is 2.2 microseconds. Okay? And a muon travels at, there we go, very, very quickly. A muon travels at 0.998 c. Even at those crazy high speeds, due to the limited amount of time that exists, if we do some basic math to figure out how far they're going to go, calculate for me real quick, how far should they make?
That length contraction.
Just how far should they go, basic math.
It should go
658,680,000.
Simplify.
2.9. No, there's a micro there. Never mind.
I do want this in meters. I don't want this in a fraction. Please do it. Please don't just sit there. Please.
You said, can we put it in microseconds? Or do you want us to convert?
Well, that's not micro, so I would not.
Or nano? Or...
No, I'm sorry. That is micro. My apologies. Yeah, you should put no. You should leave it as seconds. Actually, I want this final answer in meters. So, how far does it make it? Three sig figs. What do you got?
659.
Yeah. So what's the problem with that? Should we ever actually experience muons on Earth? No. But we measure them all the time. Should they even get anywhere close to the surface of Earth? No. But we experience them all the time. So let's talk about two different perspectives. For starters, let's begin with our perspective. Okay? 2.2 microseconds is the chemist's measuring of the lifetime of the muon. Who is at rest to the lifetime of the muon?
No, the muon.
The muon would be excess. Here's another way to say it. Who is at rest to your lifetime? There's only one individual. You. So who's at rest to that? That would be the muon. And therefore, what do they experience in terms of time?
Experience time proper.
They would experience time proper. So time proper is 2.2 microseconds. So calculate for me then, if you would, what should we experience as the lifetime of the muon? Please do it. What's the first thing you're going to want to calculate?
1 minus the 0.998
What's that called?
we were given.
Gamma.
Gamma is the letter. I don't think I told you this the other day. It's the time dilation factor is what it's regularly referred to as. But yeah, time dilation factor or gamma.
I got it.
What's gamma?
22.36.
That seems big.
I said it was 0.998 C.
I could be wrong. I thought that was yeah.
Oh, yeah, it is big. I didn't do the squares. Yep.
0.998 squared. 1 minus that. Square root the whole thing. Then invert the whole thing. Yeah, what'd you get? Not 22.
Square, yeah.
15.8, correct? And so what is the time that we should experience it? That still feels a little bit off. Maybe I'm wrong again. I don't know. 15.8 times 2.2. All right, I'm wrong. Oh, that's right. Yeah, 34.8 microseconds. Now, it doesn't seem like that much more because it's still in microseconds, but let's go back up and do this math again. From our perspective, if they don't exist in 2.2 microseconds, if they instead exist in 34.8 microseconds, how far can they make it?
Pretty sure that's what I got to.
No, that's. You said 1.04 times 10 to the 10th? Should be 0.998 C times 34.8 micro
It's microseconds.
seconds.
So it's a fourth.
I mean, it's -6 still.
Yeah.
So
10.
0.998 times 3 times 8 times 34.8 to the negative e to the negative 6th. I still screwed up. Where did I screw up?
So I got enough for 10,400.
Oh, I mean, that's about right. Okay, let's just say 10,400. So, now when we compare that to the distance that our atmosphere is in the air, should they hit the ground? But here's the trick. They should still hit the ground from both perspectives. One thing is not going to be true in one perspective and not in the other. They're not going to hit the ground in our perspective and somehow magically not hit the ground in their perspective. So what's different from their perspective that allows them to hit the ground?
The length of distance.
When they look at it, yes, they only exist for 2.2 microseconds, but they don't have to travel 9,000 meters. Who's at rest to the 9,000 meters? Who is sitting still when they look at the 9,000 meters? We are on Earth. So if we take that as length proper, 9,000 meters, divided by gamma, that 15.8 that you calculated earlier, when muons hit the top surface of the Earth, how far do they see the bottom of the Earth being? Only 570 meters away. So if we go back to the first calculation that I did, this is how far they should go, and yes, it is. But if they go that far, should they still be able to hit the ground if the ground is only 570 meters away?
Yep.
Yes. So this is one of the first examples of basically relativity 100% existing in our world, and are we able to measure muons on the surface of Earth even though we technically shouldn't be able to.
So, like, time proper is equal to, or time.
That's it for today.